analysis of social media posts. What I mean by geo-social media, as written in the title here, is social media posts that have an explicit geographic reference, for example, through the user's GPS location, for example. Now, what I'm going to try to do is to have a bit of a broad run over through different use cases, which span from natural disasters to health crises. And then I would have a bit of a bridge, basically, as well, from science to practice. That's what it says down there as well. So yes, multimodal analysis is something that we're very much concerned with in terms of our scientific developments. But then the question is always, how do we put this into disaster management practice to those people who work out in the field? Good. So to start off with, when we talk about big data, that's basically what we mean, and that's nothing surprising, I guess. But first of all, here on the top right-hand corner, I guess everybody knows that this is basically the Maslow pyramid of basic human needs. So we say that, first of all, we need to take care of physical needs like shelter, water, food, and so on. And then we can care about other more fulfilling things, including friendships, and up there we have self-actualization, which means we can pursue our hobbies and stuff. But then again, of course, down there, so that's this caricature. If there is no Wi-Fi connection, and then finally, if our battery dies, I mean, we need to ask some basic questions about the meaning of our life. And that portrays to some degree, I guess, our today's society. So we're continuously online, we're continuously communicating with each other on the go through mobile devices. Yes, of course, through social media, but also others. And the data which I shared, and I'm going to say a few words more in a second, on social media are manifold. So first of all, it's different modalities, like, for example, down here, which is a real use case from the nitrate explosion in Beirut a few years ago. So it's text, it's videos, it's sometimes images, and of course, we have the georeference, the geographication, and time, of course. And then again down here, so deciphering what people say on social media is always a bit tough, meaning people usually don't follow very strict grammatical rules. They don't formulate proper sentences. So the semantic analysis, understanding what actually people talk about and what they mean, is a central challenge that we're dealing with in our research as well. Let's go from the data side to the application side. I'm always reluctant to show this picture, but then again, it's 16 years old. It's from the Cologne floods in Germany in 2007. And what happens here, or what we see here, is a real disaster management process. And what people did here was to just basically print out a pretty much gigantic map, then pin it to the wall, and then just do different things with it in an analog fashion. So drawing, for example, flooded zones here, drawing different kinds of borders, marking blocked routes and bridges, for example, having these small focus maps here, pointing to let's say, post-its and writing notes on there. So this kind of way of doing things obviously raises a number of questions which are related to the up-to-dateness of the information, which deals with, let's say, cross-domain information sharing of information between institutions. And all this, I think, we can obviously tackle through, let's say, big data analysis and also digital systems in disaster management. Why am I showing this? This, to some degree, is still the practice nowadays. So yes, we as technology researchers, if you wish, data researchers, analysts, we think that it's self-evident that we're in the digital age and the digital transformation has hit us already. But then again, the practice is not there yet. And this is one of the key messages that I'm going to convey at the end as well, linking back to this very figure. So let me go a little bit into the methodology of what we're doing. Social media and crisis management. This was a few years ago when the European Commission asked us, look, we have a very good system that's working well, which is the EMS, the Emergency Management System, which is hosted by the European Commission. Now, the problem is this system works exclusively with remote sensing data, meaning satellite imagery. Now, what's the problem with this? First of all, they have a temporal lag. So let's say the orbits that satellites pass through just don't allow you to have real-time images for every point on Earth at any time. Second of all, limited resolution, that's getting better and better, obviously, but then again, lacking information for change detection. So before and after comparison is not always easily possible. And that's why the European Commission asked us to introduce a system that uses crowdsourced data, which basically offers this instant availability. So we have a stream of data that continuously comes in and we can analyze at any time. And second, we consider it in situ information. So yes, of course, this is a bit of a generalization. It may not always be true, but what you see here on the right side is that people take pictures from their immediate surroundings and post that on social media. And that's what you know, obviously. Good. There are a lot of buts in there. I'm going to tackle a few of those in this talk as well. So in terms of uncertainties, we do not always know whether people post about their immediate surroundings, whether when they post, they refer to past, present, or future events. But in general, we see that social media have developed towards a very reliable data source for disaster information when you do the analysis properly. Okay, so this is the information that we see. This was 2 years ago, floodings around the city of Salzburg. So you see, first of all, the timestamp. Second, of course, we have the geographic position. We have a description of the scene there, and we have a quite telling image there as well. Second thing, basically very similar. Flooded road here, fire brigade already being there. A little bit more text, and that's why I brought this comparison here, because semantic analysis, understanding what people talk about, is never all too easy, and varying text lengths is definitely something that we need to cope with. And then, of course, there are these kinds of things. So a collection of images, different kinds of videos, images of destruction that also are described and then located explicitly on the map and so on. And then you would see down there, it says Erfstadt, Germany, down here. So people tell us where they post from, which makes it easier for us to basically take a look where things happen. And that's the main thing that we're focusing on here. Good. So what's our main workflow of our analysis? I'm just going to generalize this here, and we can go into more detail as needed and desired during the Q&A session. So our general question is, where do relevant social media posts cluster? So the where is obviously a big one, because if we want to know where help needs to be deployed, we need to know where the disaster is striking, of course. Relevance is always a question, because people post all different kinds of things on social media. For example, about their, I don't know, food and their pets and their leisure time activities. So if we filter all that out, then we get relevant information for a certain natural disaster. And that's one of the major challenges, actually. And then the clustering means, where do we see unusually high anomalies, if you wish, that give us an indication that certain areas are very strongly affected by a natural disaster. So basically, we go from raw data to a pre-processing, so to say, routine that is a very specific, like 12-step routine that actually gives us a processable data set. Here we say topic modeling, not always the case, but the idea is that we semantically identify posts that are relevant for our use case. We do an accuracy assessment, mostly statistically, but also qualitatively. And then we do some kind of spatial analysis, like a passport analysis, for example, in which we then get a disaster footprint. So what does that look like in a concrete use case? And I'm just going to show a few here. First of all, this is 2 weeks of social media posts, in this case, tweets, in around Napa Valley in California. So you see these, first of all, daily patterns that are very characteristic. So we start from 0 basically during the night. We go up at 6 in the morning. Over lunchtime, we have this small dip here. And in the evening, until let's say 11 at night, we have a very strong spike that then falls off again. And this is a recurring pattern. And that's what we see in different uses of different technologies, including mobile phone data and others. What we also see is that during the week, people would post a little bit less than at the weekends. And then all of a sudden, we have this kind of thing here. I need to say that this anomaly is not the standard case, so to say, meaning that sometimes we have more of a sine wave, so to say, which does not give us these very strong anomalies just purely looking at the time series. Okay, yet still, if we take a look into this night here, what we see is this. Orange, the line here, would be a standard Sunday night. So starting at midnight, and then we go until 6 in the morning, not much is happening. So that's tweets per minute, about 100 or so, and then going down to basically 0. Before then, it strongly rises again when people get up. Good. Now, a week later, we see in blue the same pattern, basically, and all of a sudden, this happens. And now you can make a guess what happened there. I mean, it's written there. An earthquake happened, and with 0 minutes delay, we see this spike. So the earthquake happened at 3:20, 3:21, and that's exactly this point in time here. What does this tell us about the social phenomenon? The social phenomenon is, if I'm thrown out of bed by an earthquake of magnitude 6.2, the first thing I do before cleaning up and taking care of my safety is pulling out my phone and then tweeting or posting on the internet and social media, have you felt earthquake, the earth is shaking, and so on. Now, from a sociological and psychological point of view, that's a very interesting phenomenon. From our point of view, big data analysis, it's something that we can very well make use of, obviously. So this is the temporal view. So we see a time series that obviously has some anomalies or very strong patterns. Now, as I mentioned before, we're very much interested in the spatial view. So where do things happen? And that's what we see here on this map. What do we see? That's the output of our hotspot analysis. For those of you who are firm in data analytics and geoinformatics, this is GETIS or GI star. So this method of identifying local hotspots, meaning high clusters in red and low clusters in blue. What does it mean translated to disaster management? In red, we see areas that are affected by the disaster, in this case, the earthquake. In blue, we say, yes, people are also talking about the earthquake, but our algorithm says these areas are not affected. How do we ground truth this? We overlaid, in this case, with the earthquake footprint of the USGS, the US Geological Survey. And what they present is a map of peak ground acceleration, PGA here. So basically, how strong the Earth was shaking. And what you can see there is that the red areas that we identified are, to a great degree, nearly all of them, within this delineated earthquake footprint, and the blue ones are outside. And then we also identify these transitions from red to blue, here between Concord and Oakland, here between San Rafael and San Francisco, or between Napa and Sacramento. So what it shows is, and we have, of course, statistically proven this, is that social media and their analysis, if done properly, gives us a pretty good view of the world in a number of use cases. Good, so this was the earthquake use case. Let's see how this transfers to another one, which is a hurricane use case. In this case, basically the same methodology or very similar methodology. Again, our algorithm says Houston, Beaumont here, and the coastal areas are flooded. San Antonio here and Austin are not flooded after or as a result from the hurricane. Now, if we overlay this in green here with remote sensing based information, we see that delineated flood areas in the remote sensing imagery is very well delineated in large areas, meaning through space basically. But then again, what you see is here that in the middle of Houston, we don't see any green. So the remote sensing imagery says, no, it's not flooded here. What does it really look like in there? You can see down here, the trash bins are about a meter underwater. So this is, I think, the strength of the combination of those two approaches. First, remote sensing is very good over vast amounts of fields and area. The second thing is that in very densely populated areas, remote sensing just doesn't work well. And you see the theater district here. It's a very densely built up area with high-rise buildings. So you know how remote sensing works, obviously, that a satellite is not always in nadir position. So you have a bit of a tilted view sometimes. So basically, different kinds of physical effects like shadowing, like refraction, like reflections, like multipath effects impair the quality of the measurements. In other words, the satellite perhaps just doesn't see the ground. And this is where social media can complement very strongly, because in densely populated areas, a lot of people post. And that's what gives us a very strong statistical significance in terms of our outputs. On the other hand, of course, if something happens on, I don't know, North Pole, we won't realize this in the social media because nobody posts it. But then again, a natural or a disaster happens, as by definition, if there is a damage, either human or economic. So what do we see? Fast geolocated multimedia information. This is something that we deliver to our customers as well. So basically what we see here is the Germany and Central Europe floodings 2 years ago. You see a lot of posts. For example, a cluster of 900 here, a cluster of 2,500 here. And that's obviously the area around the Ahrtal region, which is the most affected one that we basically saw, which was flooded. And then, of course, we have this dynamic map, similar to what Antonio showed before. You can click on every single post. You have a description of the situation. You have the image directly depicted in the map. And then you have a timeline where you see what happens where, meaning how strongly the disaster develops, only by looking at social media. So this is the spatio-temporal view, so to say. What we see here is, again, the same area, Germany. You see that these hotspots, like the most affected areas in disasters, are jumping around. So over time, you have different areas that are heavily affected by a disaster. Then we zoom in a little bit. We have a different spatial resolution here, more fine-grained. And again, you can see that over time, these hotspots turn up. They remain a bit stable, and at some point, they move to other areas. So this gives disaster managers a hint of where the currently most affected areas of a disaster actually are. So that's the basics. Now, before I sketch out a few other, let's say, use cases, I would just go into the core of my presentation in terms of methodology, which is the multimodal machine learning. So what I said before is that the modes that we see in social media data is, of course, georeference, is time, is images and videos, different kinds of media, so to say, which is text and others sometimes. So the idea that we had was this. So far, we sometimes, or mostly actually, perform sequential analysis. First data crawling, then pre-processing, then semantic analysis, then spatial analysis. Now, why don't we integrate this into an integrated or multimodal model that then produces an composite view, so to say, onto the situation? So we integrate text, geolocation, time. From the text, we use semantics, we use sentiments, and others. And then we go to interpretable, let's see, multimodal classes of posts. What does that mean? From a machine learning viewpoint, that's what we do. From the input side, we have vectorized input documents, which is latitude, longitude, which is the timestamps, of course. And from the text I mentioned, we derive semantics, like semantic topics, what people talk about, and sentiments, how people feel when they talk about these topics. So these are the feature engineering processes that we basically then use for fitting a machine learning model, which is in this case a self-organizing map, basically. In this case, a geo-G-sum, which is a growing sum, and then a geosum basically puts more emphasis on the geospatial dimension. What's the fun part of a self-organizing map? The output, which is a hexagonal grid, so to say, preserves topological relations. So if you think of it as a network, nodes do not cross edges during the analysis process. Good. In the end, the clustering means that we go from an n-dimensional space, which can be more than a few hundred dimensions, into a two-dimensional space that we compress. Good. So that's the clustering feature vectors in n-dimensional space. The output is a cluster map. Yeah, map not necessarily in the cartographic sense, but still, with clear topic, sentiment, location, and time information. Good. Importantly, multi-language support is a big one here, because that's what we're strongly dealing with, especially in multinational disasters. We can basically shove in our text data in whatever language we have, and those two machine learning methods for the feature engineering process are able to deal with that. So that's the methodology. What comes out, first of all, are these kinds of topics. So you have sentiments for each topic, and that's a semantic topic, right? A group of posts, so to say, that talk about the same things. And then other relevant information would be a description of this topic. And why I brought this up here is that until now, basically over the last 10 to 15 years since we've been doing this, the output of a topic modeling method was always a list of words. Basically, as I mentioned down here, single words that define a topic that are associated with a semantic topic. For the earthquake topic, for example, you would have earthquake and shake, and the earth is shaking and so on. Whereas for a flood topic, you would have water and flooding and rescue and all others, and all different kinds of words. Now, from these single words, we so far had to extract meaning. So what are people actually talking about? How do we interpret this, and what do we tell disaster managers? Now, through the rise of generative textual machine learning models, in this case, Llama 2, we are able to label topics in an automated fashion. So what is here is the output of the generative text model, in which we input all the posts that belong to this very topic. And that's the final geospatial part, because that's in the end what disaster managers are interested in. Where are these topics located in geographic space? And then you can see that, for example, topic number 76 here, people talk mostly about where the disasters and everyday struggles. So they need help, they need rescue, they don't have water, they don't have electricity, and these kinds of things. As you see over here, this is a negative cluster, meaning negative sentiment. People are scared, people are frightened, people are sad. Same thing down here. Flood disaster and government criticism. In this area, people mostly talk about politics, about policy making, and how politics has not prevented this disaster and how badly the disaster is managed. So this was the real world situation. So in the end, what you see here is that we have a number of topics that are spatially distinct, that talk about different things, and that change over time, obviously. And this is a, I don't know, kind of hotspot map that helps disaster managers and policymakers to really get people the type of help that they actually need. Good, so this was the multimodal machine learning approach. Now, in the second part here, I would like to just go through a few other use cases, which first of all is spatiotemporal epidemiology. So we go from natural disasters to health-related issues. Here, what we see is a time series of COVID-19 related posts. First of all, here in the US, but then you see in the DACH region, so Germany, Austria, and Switzerland, it's pretty much the same pattern. It's very similar. And then what you see is that you have these rises here, then up here, and then the big one up here, which is basically very strongly correlated with different kinds of events. So for example, the WHO announcing a public health emergency of international concern here. 3 weeks later, announcing a potential pandemic, and the CDC, the Center for Disease Control in the US, issued a warning. And then the WHO declared a pandemic, and that's the important thing here. You see that the Twitter wave basically overtakes the epidemiological wave at some point. So here, the tweets were rising heavily already 3 to 4 days before the WHO declared the pandemic. And in this publication here that we did together with Harvard Medical School, we basically showed that this Twitter wave is about 14 to 17 days ahead of the actual case curve. In other words, let's look at this. In blue down here, you again see the Twitter curve for COVID-19. And in orange, you see the daily new confirmed cases. So the rise here between the blue and the orange curve is very, very similar. But then again, you see that the orange curve lags temporarily by about 14 to 17 days. Again, what does that mean? If we know that there is a rise in social media, we can expect a rise in cases 2.5 weeks later. Good. This was a temporal view. That's a spatial temporal view, a spatial view again. Good. So you see that here in the beginning of 2020, not much happened yet. In yellow, basically what you see is very, let's say, non-significant areas, meaning we're not sure what happens there, but basically it's probably nothing. And then as posts start to densify, you realize that these hotspots that we saw before for the earthquake as well, for example, start building up. For example, up here. So upstate New York, this very strong hotspot, then down here around LA, then around Alabama, and then in Montana, Wyoming here, you have the cold spot. And this is an important one where we also work together with Johnson & Johnson, for example, so a pharma company in the US. And they would ask us, where can we expect high incidence rates, like high prevalence of the virus, in 2 to 3 weeks? Because what they want to know is, we have 30 test centers in the US, and when we vaccinate people to test our vaccine, we need to make sure that these people are also exposed to the virus, right? Otherwise, we don't know about its efficacy. And that's exactly the combination between the temporal view, yes, it's 2 to 3 weeks ahead, and the spatial view, where exactly can we expect the hotspots? Good. And the third use case I'd like to present is humanitarian safety. I guess you all witnessed what happens and happened, and this will, of course, intensify in the future as well. On the right side here, you see pictures from Salzburg. So this is the main station a few years ago. And this here is basically 3 kilometers further, which is directly at the Austrian-German border, where people just got stranded because Germany in the end closed the borders. So these intensified refugee movements really put crisis managers through very, very tough times and in front of heavy challenges. And our goal here is obviously to ensure humanitarian safety through better reception, transfer, and supply, and accommodation of refugees. Meaning, if humanitarian aid organizations know when, how many people arrive, and what needs they have, they can prepare accordingly. How many meals do I need? How many blankets do I need? How many diapers, sanitary articles, tents, all different kinds of things. Good. And the idea is still the same. We see a change of the spatial focus areas over time. In other words, which refugee routes are frequented in which way, and we show this again through hotspots. So for example, here we see this the start in 2020. What you see in the beginning basically here is that the area down here, so this is the Turkish-Greek border, is very strongly frequented, mostly on the Turkish side. And then a little bit later, things start moving up to the Balkan countries, and then it swaps over very strongly for a hotspot in the Serbian-Hungarian border region. And then you see that people start crossing into Austria, for example. So this is a daily visualization. And then you remember that Hungary built their infamous fence here, so towards Serbia. So people in the end took a detour through Slovenia and into Austria through the southern border, which we see again towards the later stages of exactly here of this time series. So if we take a look at the use cases, it's always the same. The idea is we take a look into a remote situation without actually having to be there, but still getting a very good idea of what's happening. Just a few anecdotes. One rescue organization was calling me Saturday night, 9:30, and they said, look, we heard by our informants that Erdogan, Turkish president, is opening the border towards Greece, and we expect 250,000 people at the Hungarian-Austrian border here in 4 days. Is that true or not? And then we take a look into the data, we take the live stream, analyze it, and then we say, probably not happening. The same thing with the Beirut explosion 3 years ago. People didn't know what happened there. So was this an explosion? Was it a gas leak? Was it a terror attack? What happened there? Second of all, what do I need to send there? Is it rescue dogs or search dogs? Is it doctors? Is it heavy gear in terms of machinery? Is it food? Like, what do I actually need there if I want to go there as a humanitarian aid organization? And that's exactly what we then elaborated with them. So within, 1-2 hours, we had a very good view of what happened in Beirut. You saw that the entire city was basically, the inner city was pretty much flat. And then through drone footage and images and textual descriptions, we got a very quick overview of what happens there. And that's how then rescue organizations plan their missions. And then, of course, we have these tracks. Now you see what you saw so far is moving hotspots, basically. So hotspots appear at different places over time, which can usually be also trajectories. Here, we see that many people either have produced trajectories their own, so they are spotted here first and here 2 days later. And second, they would also describe things like, I'm just photographing 2,500 people boarding the train from Budapest, Hungary to Vienna, Austria, and these kinds of things. So verbal description of the situation. And then you can build this origin destination maps, so a chord diagram in this case, where you can see the flow of people. So from Greece into Northern Macedonia into Serbia, Croatia then here into Slovenia, and then of course further into Budapest and Hungary. And then you see that the big outgoing arrow here from Hungary is to Austria, and then from Austria further Germany. So this is a temporal sequence, so to say, of mass movements that we have been witnessing by purely looking at social media posts. Now, the last part of my quick presentation here is the practice. So we go from the scientific methods that I presented before into practice. What did we do a few months ago? We had a disaster management exercise in Salzburg, with 900 action forces in 4 disaster areas, which I'm going to present in a second. And we had a realistic crisis management board. So these were the crisis managers that are basically responsible for different kinds of things. Like, one person is there to assess what's happening out in the field, the situation. One person is there for resources. One person is there for press management, for ICT, all different kinds of things. These were the rescue organizations and crisis managers involved. Here you see all the regional heads of the Red Cross, the police, the fire brigade, the water rescue, and others. And the idea was that we build up a very digital, obviously, crisis management room, which is not usually the case. As I mentioned in the beginning, crisis managers at times are still working very strongly with analog means. Digital crisis management center we built up, and the goal was to evaluate the usefulness and the usability of the information layers that we produced. Good. The goal was this: analyzing heterogeneous big data sources and automate the analysis of Earth observation and web data, and like this, quantify the spatial extent of the affected areas, as I mentioned before. Let me quickly say a few words on the action areas. Afterwards, I will go quickly into the data sets that we used. Cool. So you see the city of Salzburg here, and in red, you see the crisis areas in the vicinity here, and here of Salzburg, and then in the middle of Salzburg city. Which were, first of all, near Oberndorf here, we had people spotted in river, which were basically flooded into the river, which had been rescued by the water rescue. In Seekirchen, we had a lake where we simulated flooded buildings and also cars that were pulled into the lake. In the city of Salzburg, a building collapsed, so we used a demolished building from a public authority. And then here in Kuchel, around the train station, we simulated a derailed train. The train was provided here by the Austrian Railway Services, and the scenario was that this was a dangerous goods train. So we had CBRN units there together with the fire brigade and the Red Cross. What are the data sets we used? Social media hotspots I talked about. So you see first out here, the flooded area here. Then the hotspot moves into the city of Salzburg more strongly over time here. Then we see it down here in the area of the derailed train, and up here also with the people who were washed into the river. So I'm probably changing spatial disaster areas as hotspots. And together with this, we presented single posts, so like this one. A person in the city of Seekirchen, which is outside Salzburg, seeing this flooded area here, and just like this over here as well. Good. Together with this social media information we got from different APIs, and I can say a few words about the data in a second then as well. We had live reporters in the field as well. So people out there were photographing the scene, putting this on social media, and from the social media channels, these people were directly integrated in the common operational picture in the crisis management room. Furthermore, we used radar satellites to basically delineate flooded areas, which you see here in blue. So this, in bright blue, you have these non-permanent water bodies, so to say, that were simulated. Here in these four areas again that I presented before. Good. Then optical satellite and drone imagery. So what we see here first is in the city of Salzburg and in the city of Kuchel, which was the train incident here, a satellite image from 3 years ago. Then an up-to-date satellite image. So you see that the building has collapsed already here. And this you will see in the next slide as well. And then a very up-to-date drone image. We see the high resolution already, and that you see the damages of the building already. Good. Then from this, we detected, first of all, buildings in yellow and vehicles, cars mostly, in blue. And this information was also fed. And then we tried to fuse this information, namely the floodwater masks, the hotspots from social media, and then demographic data to really assess where, let's say, most people would be affected through the disaster. And then on the right-hand side here, you see the disaster hotspots that again change over time. Good. Then, of course, we had a digital 3D model where you can pinpoint. You see the damaged building here. You can zoom into that, so to say. There are different kinds of measuring tools included and so on. So that's the damaged building or collapsed building that we used for our exercise as well. This is where we use this 3D model together with the heads of the rescue organizations. This is an image from the collapsed building with rescue dogs and so on as well. That, again, the situational awareness room, and here the derailed train, basically, with the accident. I would just like to show a very quick video that we did so that you get an impression of what really happened there. So this was the lake outside the city where we brought in basically groups that people were rescued from helicopters. This was the crisis management. Sorry about this. So here you see the head of the crisis management board, and then the people working with our system, and then using the information that we provide them with to actually handle the disaster. And this was the situational awareness room, so to say. People flooded like on houses and fled on their roofs, so to say. Then injured people having to be rescued from roofs and their let's say rooms as well. Now this is the head of the regional Red Cross. Basically, what he's saying that the AI information is very much helping them to understand and to cope with the situation. Live images. This is the head of disaster management for the region of Salzburg. So he says in 3 ways there is what helps them. First of all, these live drone images that they use a lot. And of course, the social media hotspots that we provided, and then the satellite images that provide flood-related disaster management information. Yes, for me, it was more like the let's say, transition from basic science to practice. So what we usually do is we write papers with a lot of formulas in there. But then again, how do we get all this into practice with people who are not really working with up-to-date technology, who are not firm in scientific methods, but who really, like here, rescue people out in the field? And that's what they say as well, that it was a privilege for them to work with us and to be part of the exercise. Again, you see that it's quite realistic. So it's a lot happening there. It was a bit of a stressful event. Let's say, fortunately, not too many people got hurt, because from 900 people in somewhat realistic scenarios, some injuries also happen. Good. So back to the presentation. Quick wrap up here. First of all, what I want to say about geosocial media analytics in action, in practice, is that we see that we have worldwide availability. So the idea here is that we basically scan the entire world continuously in a number of geosocial media channels. And this can be Twitter, X, this can be Instagram, this can be Facebook, this is Telegram, this is Reddit. Partly, this is also public WhatsApp groups. Of course, Flickr and Foursquare, which have nice APIs, but which are not used so much anymore. And which is YouTube, importantly, which gives us a very good idea of what happens out in the wild, so to say, because you have geo-referenced videos. So people tag where they are, and then they, for example, hold the camera against flooded areas, which gives us a very good indication of what happens there, even better when they also describe what you see in the video. So basically model the spatial spread of crisis situations, so how the spatial situation, how affected areas develop over time. The great thing is we have a continuous data stream, so we can basically use these data at any time for real-time situation reports. So you see that people are basically reporting in somewhat real time continuously. The initial installation takes usually a few hours, but then again, if we professionalize this can be easily driven down to 1 hour. And the maximum update frequency depends strongly on the data density. So for example, in the US, we have a lot of data, and we can basically do, 5-minute wise hotspot analysis. Depending on where we are in the world, people post more or less, and this is why we have more or less data. We may drive this, for example, up to half hourly in the update frequency. Information visualization is one of the big questions. We just had a consortium meeting today as well with the Red Cross, with the Fire Brigade, and with others, where there's always this gap between what we output and what people want to see in the disaster management process. So when we tell them, look, we have these 5, 6, 7 different data sources, and then we have geosocial media and remote sensing imagery and mobile phone data in this case as well, like where people densities are unusually high and so on. They are like, look, in our system, we do not want to have 23 instead of 13 information layers. But what I want to see is here is red and here is green. And where is red, I look into, and then I see I need to take action there. Because when people are under stress, and that's what happens in disaster management situations, obviously, they will not be able to look at 5 different information layers, extract information from that, do the transfer process, let's say, abstracting the information and converting these into disaster management action. Furthermore, we are very well transferable between use cases and geographic regions. You saw that we were in the US, in Germany, in Austria, all different kinds of regions in the world. We're also working with CDC Africa, for example, where we're doing work in Congo for different diseases like yellow fever, like Ebola, and others. So it's very well transferable between use cases and geographies. And then, of course, the integration into information, into disaster management processes is technically rather simple. Also from what Antonio presented before. We have highly standardized interfaces. We provide the information. Disaster management agencies can pull it from there or can just take it from there and integrate those into their disaster management processes. And now comes the but, and that's my final claim here. How do we go from research into practice? I think, and we're pretty confident there, our information products are good enough, are far enough, are mature enough to be used in practice. And that's what we have found in about 15 to 20 real-world use cases. Again, as I mentioned, from epidemiology in the US, in Germany, Austria, in Nigeria and Congo, in the Bergkarabakh conflict, Azerbaijan, Armenia, in the refugee situation 2015-16, in the refugee situation in Afghanistan, then in the conflict zone in Ukraine, Russia, and so on. So we're there, the information is usable, it's also requested by disaster management agencies, with the but that the challenge is still that we efficiently use this digital information in the disaster management process. And what we need, therefore, is a digital transformation, really, of the disaster management process, really putting things to the computer. Some people are very conservative for good reasons sometimes as well, that they say, okay, what if a blackout happens? What do I do? I cannot use digital information anymore, can I? And that's a valid point, obviously, there. But then again, for me, this is not a reason not to use digital information at all, but you can always have a fallback strategy to analog information. How do we do this? My take on this would be, the goal is the integration into the disaster management processes through continuous training. So if you have never looked at a moving hotspot, if you have never seen an output of a multimodal machine learning model, you will not use it in a crisis management situation. Of course not. But then again, if you train this like 3, 4, 5 times a year in very specific scenarios, which could be large-scale efforts, which could be large-scale events, which could be demonstrations, refugee situations, natural disasters, then at some point you will get used to that, and the information will be usable in real-world disaster management processes. Good, so this was my quick overview about what we're doing. Multimodal analysis, so you remember we have the multiple modes or modalities in the social media data, like geospatial, time, text, semantics, and sentiment, plus again, of course, images and videos, and how we try to bring this into practice from our scientific methods. Good. Thank you very much for inviting me again and for being here. And I'm very much happy, obviously, to take your questions. Thank you.
Thank you a lot for joining, Bernd. I don't see any questions. It was a very nice presentation. Oh, there is a question.
I have one.
Yeah.
Are you filtering fake info? This is a very, very good and an absolutely valid question. Yes, we do, but it's not our research. Let me put it like this. Fake news, fake information is really, really hard to detect. And if you want to do research in this area, you need to fully subscribe to that, because there is a number of, let's say, plausibility metrics, statistical that you can use, but none of them works really well. So what we do here is that we just rely on other people's research and their outputs, we use their libraries and methods, but we do not develop them ourselves, because this is an effort which is extremely complex and which would be out of scope, unfortunately, I need to say, for us, but this is a very big one. A bit of a bold answer that is a bit shallow and not entirely true is that our argument is that we have so many data sets, which is millions and millions of posts usually. So this gives us some statistical robustness. If we say that hotspots appear here and the hotspot is a result of tens and hundreds of thousands of posts, then we can be pretty sure that what the posts say is actually happening there on scene. Vice versa, if, I don't know, 1, 5, 10 people spread fake information heavily, we still argue that this vanishes somewhere in the statistical properties of our data set. So far, it has worked pretty well. But of course, I have no very strong proof at the moment for what I've just been saying. Good. Then